Before we even reach the event horizon, we need to understand something deeper: entropy. In everyday language, entropy is often described as disorder. But in physics, it's not about messiness. It's about information. Entropy measures how many possible microscopic configurations could result in the same macroscopic state. The more possibilities, the higher the entropy. Imagine a deck of cards, perfectly ordered, lowest entropy. Shuffle it thoroughly, high entropy. The arrangement is now unpredictable. In thermodynamics, entropy explains why time flows forward, why heat moves from hot to cold, why stars die, and why your coffee cools. It's the cosmic arrow of time. Every moment, the universe chooses from trillions of possibilities and always slides toward more. So when we talk about black hole entropy, we're not just talking about heat or disorder. We're talking about cosmic bookkeeping, the information encoded in the fabric of space-time itself.
Here's the cosmic twist. In 1972, physicist Jacob Beckenstein proposed something radical. He asked, if black holes erase everything, doesn't that violate the second law of thermodynamics? If you throw a cup of tea into a black hole, its heat, its entropy all vanish. But that breaks physics. Entropy shouldn't decrease. So Beckenstein made a bold move. He argued that black holes must themselves have entropy, not zero, but enormous. And he even proposed a formula for it, linking the entropy to the area of the event horizon, not the volume. That was weird. All other systems scale with volume. This was the beginning of the black hole information paradox, a foundational problem that would haunt physics for the next 5 decades. If a black hole has entropy, it must have temperature. But black holes don't radiate, right? Enter Stephen Hawking. In 1974, using quantum mechanics near the event horizon, Hawking showed black holes do radiate. This Hawking radiation was the missing piece. Black holes aren't perfectly black. They leak, they lose mass, they evaporate. But this raises the stakes. If black holes evaporate, what happens to the information? The atoms, particles, and memories that fell in, are they just gone? If so, that's a fatal blow to quantum mechanics, which demands information is preserved. And so we entered the greatest mystery in modern physics. Is the universe erasing its own memory?
Black holes were supposed to be the perfect prisons. No light, no energy, no escape. And yet in 1974, Stephen Hawking looked at the edge of the abyss and saw a flicker. Using quantum field theory and curved space-time, Hawking showed that near the event horizon, particle-antiparticle pairs constantly pop into existence, a consequence of quantum uncertainty. Normally, they annihilate and vanish again, in an instant. But near a black hole's event horizon, something strange happens. One particle falls in, the other escapes. To an outside observer, it looks like the black hole is radiating energy. It glows. Dimly, faintly, but undeniably. This became known as Hawking radiation. Here's the mind-bender. That escaping particle has to come from somewhere. The black hole loses a tiny bit of its mass to account for it. Over billions of years, the black hole shrinks, evaporates, disappears. But if it disappears, what happens to the information that fell in? The matter? The photons? The particles? The structure? All of it should, according to quantum mechanics, be preserved. But in a fully evaporated black hole, it seems to be lost. This is the information paradox. It's like the universe shredded its own history and burned the pieces. And this paradox, it doesn't just challenge physics. It challenges the very idea of cause and effect, of predictability, of reality itself.
Imagine this. Everything that happens inside a black hole, all the particles, gravity, motion, energy, is somehow fully encoded on the surface of the event horizon. Not inside, outside. This is the heart of what we now call the holographic principle. Proposed in the 1990s by Gerardin Toft and Leonard Susskind, this principle was inspired by a strange realization about black hole entropy. The amount of information a black hole holds is proportional not to its volume, but to the area of its event horizon. It's like finding out the content of a book isn't written on the pages, but on the cover. This flips everything we know about space and matter. If all the information in a region of space can be encoded on its boundary, then maybe, just maybe, our entire universe is a projection. A 3D reality emerging from 2D information. Sound crazy? Consider this. The math behind black holes in a curved space exactly matches the math behind quantum theories on a flat surface. It's like two completely different worlds. Gravity and quantum mechanics are secretly speaking the same language, just through a mirror. In string theory, this becomes the famous ADS-CFT correspondence, where a 5-dimensional gravity universe maps perfectly onto a 4-dimensional quantum field theory with no gravity at all. A shadow reality, a cosmic hologram. And if that's true for black holes, could it be true for us? Could everything you see, everything you touch, even your own thoughts, be echoes on a distant surface?
Why does time only move forward? Why do we remember the past, but not the future? It all comes down to entropy. Entropy, the measure of disorder, gives time its direction. A glass shatters, but never unshatters. Heat spreads, never gathers. The universe expands, ages, forgets. This is the arrow of time, not a mechanical law, but a statistical tendency, a cosmic tide. Black holes, it turns out, are part of that same flow. When something falls into a black hole, the black hole's entropy increases. Its surface area grows. That surface, the event horizon, becomes a record, a scratch mark on the flow of time. Here's the astonishing part. The second law of thermodynamics, which says entropy always increases, seems to hold even in the presence of black holes, so long as we count black hole entropy as part of the equation. It's as if the universe said, even here, in the darkest places, the rules of disorder still apply. But black holes do something stranger. They seem to push entropy to the edge of physics. They maximize it. For a given volume, no object has more entropy than a black hole. That means, of all the ways the universe could stuff information into a region of space, the most efficient, the most chaotic, is to collapse it into a black hole. This connects gravity to information to time, and maybe to the very origin of the cosmos. Because here's the twist. If entropy gives us the arrow of time, then the early universe, smooth, uniform, low entropy, was an impossibly special moment. And black holes, they may be the cosmic counterweight, the final stop, where entropy concentrates, like ink blotting the pages of time. What does that say about our beginning and our end?
Imagine falling into a black hole. For decades, general relativity said you wouldn't feel anything crossing the event horizon. No sudden flash, no burn. You'd float past it peacefully until gravity ripped you apart deeper in. But in 2012, a bombshell hit the physics world. Some theorists argued that quantum mechanics demands something else, a firewall, a searing, energetic wall of destruction at the horizon. Not a peaceful crossing, but instant obliteration. Why? Because quantum information, according to Hawking, leaks out of black holes over time through radiation. But quantum theory also demands that information not be cloned. If it exists in Hawking radiation outside, it can't also still exist inside the black hole. Something has to give. So physicists were faced with a horrifying choice: break general relativity, allow a firewall with the horizon; break quantum mechanics, allow information to be destroyed; or break the rules of locality, meaning things happening here might instantly affect distant regions of space. This is the black hole firewall paradox, and it shook the foundations of physics. But there's more. Black holes are now thought to be quantum scramblers, nature's fastest destroyers of orderly information. Throw in a particle with a simple pattern, and within milliseconds, it's been spread out across the black hole's surface in an unrecognizable tangle. It's not lost, but it's buried so deeply in noise, it might as well be. This scrambling power isn't just terrifying, it's useful. Some physicists think it could teach us how to build better encryption or even faster quantum computers. In fact, one of the best models of black hole scrambling uses a type of quantum circuit we call the SYK model, a random soup of interactions that mirrors how black holes dissolve order. It's as if black holes aren't just cosmic prisons. They're computers, maybe even the ultimate computers. But if they process information, can we ever read the results? Or is the truth of the universe scrambled forever?
Let's go back to the central mystery. What happens to information that falls into a black hole? Hawking's original argument in the 1970s said, it's gone, evaporated, lost forever as thermal radiation. But that's a problem, because quantum mechanics, our most trusted theory of the microscopic world, demands that information is conserved. It cannot be destroyed. If you know everything about a system now, you can, in theory, work backwards to see how it got here. But if black holes erase information, quantum mechanics crumbles. So what gives? This is the black hole information paradox, and it haunted physics for decades. Enter new ideas. In the last 2 decades, progress exploded. String theory, holography, quantum entanglement, all started offering hints. Maybe the information does escape, encoded subtly in Hawking radiation. But the process is so tangled, so chaotic, that it looks random unless you know everything. Physicists like Juan Maldacena and Stephen H.S.U. suggested, what if the inside and outside of a black hole are entangled in a weird mirror-like way? That the information falling in doesn't vanish. It's mirrored on the event horizon and slowly leaks out as the black hole shrinks. This brings us to the concept of unitarity, the idea that all quantum processes, even black holes, must preserve information. No exceptions. More recently, researchers proposed the page curve, a prediction of how information should flow out of a black hole over time. And surprise, the latest studies using quantum gravity models and holography show that this curve can be reproduced. The implication?
Hawking was half right. Black holes do radiate. But he was wrong about the information being lost. It's there, hidden, encoded, not gone, just scrambled. This is revolutionary. It suggests we can trust quantum mechanics and explain black holes. But does that mean a theory of quantum gravity is within reach? Or are we just scratching the surface of something even deeper?
Black holes have no hair. It's a phrase you'll hear again and again in theoretical physics. Coined by John Wheeler and others, it means this. Once something falls into a black hole, a star, a planet, a book, a person, the black hole forgets all details. It remembers only three things: mass, electric charge, and angular momentum. That's it. Everything else, shape, structure, composition, complexity, vanishes. From the outside, two black holes of equal mass, charge, and spin look exactly the same no matter what created them. This is the no-hair theorem. And it's elegant, but also deeply unsettling. It means black holes erase identity. They reduce everything to bland sameness. It's like blending every book in a library and keeping only the weight. But remember what we just learned in the last chapter. If information is not destroyed, then somewhere, somehow, a black hole must carry the fingerprint of what it swallowed. So the question arises, do black holes have hair after all? Not literal hair, of course, but quantum signatures, complex microstates, or holographic imprints that preserve information in ways we don't fully understand yet. In string theory, some researchers propose that every black hole corresponds to a vast number of microstates, distinct internal configurations that are invisible from the outside but preserve the identity of the matter that fell in. These ideas suggest black holes do have hair, just not classical Einstein-style hair. It's subtle, quantum, maybe even holographic. So the no-hair theorem isn't exactly wrong, it's just balding in higher dimensions. And if black holes do have identity, then who or what is keeping track? Is it the event horizon, the radiation, the quantum fabric of space-time itself? Or are we missing a layer of the universe's memory?
The holographic principle. Is the universe a black hole? Let's zoom out. Way out. We've been talking about black holes as strange, extreme objects. But what if they aren't exceptions? What if they are the blueprint? In the 1990s, physicists like Gerard, 't Hooft, and Leonard Susskind proposed something radical: that the entire universe might work like a hologram. Not the sci-fi kind, but the physics kind. Here's the idea. Take a 3D object, like a black hole. Its entropy, as we learned earlier, scales with its surface area, not its volume. This is weird. Most things in nature scale with volume. You double the size, you get 8 times the stuff. But black holes, double the radius, and the information only increases by a factor of 4. It's like all the information about what's inside the black hole is somehow encoded on its outer surface, the event horizon. This led to the holographic principle. In a quantum gravitational system, everything that happens inside a region of space can be described by information stored on its boundary. Think of a 2D surface projecting a 3D reality, just like a hologram. And here's where it gets wild. Some physicists now believe this may not just apply to black holes, but to the entire universe. That our 3D reality, space, time, matter, everything you touch and feel, might be a projection from a distant, lower dimensional surface we can't directly observe. In string theory, this shows up in a model called ADS-CFT correspondence, where gravity in a volume of space is equivalent to a quantum field theory on its boundary. This isn't just mathematical wizardry, it might solve the information paradox. It might unite general relativity and quantum mechanics. It might explain why the universe has the shape and structure it does. And it might mean you, your thoughts, your body, your memories are part of a vast cosmic hologram. The holographic principle is the universe a black hole? A black hole not as a prison, but as a mirror. So here we are, from collapsed stars to cosmic codes. From entropy to existence. Black holes, once symbols of doom, now seem to be gateways to deeper understanding. Maybe they're not the end. Maybe they're the beginning of a new way to understand everything.